I think a few more people will probably join us as we get started. So today, I think it's going to be a little bit of a hodgepodge, kind of all over the place kind of lecture, because there are a number of odds and ends that I kind of want to tie up as we start to move forward into Lab 4. So we're doing Lab 3 week 1 checkouts will conclude today with the Wednesday folks, which means Lab 3 week 2 checkouts will start on Monday for the Monday people, which means on Monday the Monday people will also ostensibly be starting Lab 4. So Friday seems like the right time to start talking about Lab 4, which means today is the last day to really talk about Lab 3. So I have a list that I want to start with of just sort of all of the various bugs that we've encountered in Lab 3. And some of you, these are going to be familiar because we've been working through them, but it occurs to me that for others of you, you may not necessarily have avoided these bugs consciously, but just kind of dodged a bullet, which doesn't necessarily give you armor against that bullet in the future. So perhaps it's a good idea to just go through all the issues that folks have encountered and talk through them a little bit. And then because the last lecture got a little abbreviated and weird because of the technical difficulties, I want to just revisit a couple of those topics with the slides that I intended to go with them, just to hopefully maybe clarify a few things. And then with time remaining, I want to talk a little bit just about end of semester sort of logistics as we start thinking about transitioning into final project mode, because that's coming up pretty soon. And well, I'll talk about this at the end of the lecture, but usually in this class we'll do a lecture for lab transition at some point in the next couple of weeks, where we'll substitute more lab time in place of this lecture time, because at that point in the semester, usually that's the way to be most helpful to folks, is just to spend more time with them in lab. But in any case, we'll talk about that. So let me start by just going through some of these bugs, and I suppose I'll share my screen and just write these out so that we can talk through them. Let's see, I'll share that window in particular. Okay, can folks see that? Yeah. So we saw a lot of trickier than previous lab bugs in this lab. So I feel like a conversation like this makes sense. Some of these are just kind of no-brainers, that they happen to you once and then they won't happen to you again, and others of them are a little bit more subtle. The first thing I'll mention is a number of you are using the memcopy function to copy. You have your code set up in a way that you are populating some array of samples in an interrupt service routine, signaling to a thread that you're finished populating that array, and then copying that thread to a thread that you'll pass the FFT function in the threaded part of your program as opposed to the ISR. And you're doing that by means of a memcopy function call, which generally speaking is a good idea. The alternative to this would be to loop through in a for loop and copy it index by index. And it's not always clear which of these two options is faster. Generally speaking, memcopy is a highly optimized function for doing specifically that thing, which is move data from one array to another array, or one place in memory to another place in memory. So it will, generally speaking, it will always be as fast as looping through a for loop, and it may be faster, depending on the compiler optimizations. Neither is as fast as a DMA copy, but you don't have to do that in this slide. That's just something to keep in mind. But the bug that we encountered is to remember that memcopy, one of the arguments to memcopy is the amount of memory to pass, and it takes that argument in units of bytes. So memcopy takes amount of data as an argument in bytes. That was one bug. It took us a little while to track that down. The other one, this one's a little bit more subtle, is a number of you have encountered this issue where you start playing a sound into the PIC32 and it starts resetting over and over and over again. And that can be a symptom of a number of different things. In previous labs, that's been a symptom of dividing by 0. Bruce made a list of other stuff that can cause persistent resets. If you have the volume on your lab PC too high, so that you're sending voltages that exceed the range of the ADC into the ADC, a symptom of that we have discovered is the CPU will reset over and over again. The exact mechanism by which that occurs is not clear to me yet. Maybe Bruce knows.
I have a hypothesis about that. I'm not completely convinced, but I think it is that the brownout circuitry on the CPU looks for over voltages and under voltages rather carefully. And when you exceed the input range of if you exceed the power supply ranges, there's a protection diode which shorts the input voltage to VDD. If it's a low enough impedance source, it'll push VDD up a little bit, and the CPU power regulator says, uh-oh, and resets.
Okay.
That's only my hypothesis. It has to do with the internal protection circuitry, because as you may remember from some course, if you exceed the input on a CMOS gate, if the input exceeds the rails, the CMOS gate turns into a silicon controlled rectifier and destroys itself.
So use your attached picos. So first of all, make sure that you've asked that we move your scope probe to the analog input. For almost every group, I think we have. If you haven't asked for us to do that, then we may not have done that yet. But check the voltage levels on the oscilloscope and change the volume of the lab PC until it's comfortably within the range of 0 to 3.3 volts, and it's not exceeding 3.3 volts. The other thing to be careful to just mention is to be careful of type. This has been true in all labs. Type meaning like int versus a cum, data type, particularly in the FFT function. And in fact, let me pull up the lab right up and show you there's a particular line in here that has been causing folks some trouble. And my suspicion is that if you are starting with the demo code that shows how to use the FFT, that's one version of this function, which is a slightly different version of the function that is provided in this lab write-up. As I mentioned here, this function uses a cum, that other type uses a fix14, which is defined in that script. In any case, if you are using a cum fixed point data types, which is what I recommend, which is what I think everyone is doing, be certain that these variables here are of type a cum. These are just incrementing variables, so it's fine to have those be ints. These, however, are being used to calculate the FFT, and they're working with the real and imaginary arrays that you put in, which are of type a cum. So be certain that these are of type a cum. Okay. And I mentioned this a couple lectures ago, but I've gotten a couple questions about it, so I will mention it briefly again. These begins and ends, if you look at the top of the demo code, they are just pound defined as open curly brace and close curly brace. So you can replace a begin with an open curly brace and an end with a closed curly brace, if you would like to. Okay.
I saw another error a couple of times in the FFT, and that is that people would declare the sign table, but not actually populate it with sign values. The effect is that C initializes the sign table to 0, and so the output of your FFT is 0.
And be aware too that I think in lab 1, the example code called the sign table sign_table. Just be aware that this function, when it goes to look for the sign table, it's looking for an array called sine wave. So you can either change the name of this array in the FFT, or you can change the global name of the array where you're storing the sign table, but just make sure that the names agree. If you are combining code, you make sure that the code all agrees with itself, and this is one of the globals that this function is looking for, is that sign table. Are there questions, any questions about using this function? People seem to be doing okay with it. There are a few other things I'm going to mention about it as other bugs, but if there are other questions, you can just interrupt me. Yeah, the other thing I wanted to mention, I've seen this in a few groups, is um, I have pointed you to two pieces of code as recommended starting places. One of the pieces of starting place code is the example on the DDS page that draws an FFT, and that's to see how to pass inputs and get outputs out of that FFT function. And the other piece of example code is the examples listed on the ADC page on the course website, which shows you how to set up the ADC and read it in software as opposed to DMA. Be aware that you must change if you are using the FFT example code as a starting place, you need to change the drawing part of that code. Remember that code is drawing an FFT, so it's treating the magnitude of the complex outputs of the FFT function as essentially y coordinates, and it's plotting a function. For the spectrogram, just remember that the magnitude does not map to a coordinate, it maps to a color. So you'll move incrementally across the screen, so your x coordinate will be the same for all, for a particular update of the spectrogram, all of your x coordinates are the same. In the next update, they increment by 1, you move to the next pixel. Your y coordinate will be essentially just the index of the output array, because that maps to frequency. And then the color of the pixel is related to magnitude. So you must change the drawing code in the FFT example.
There is also one setup parameter in the ADC code. It is param1. The second option in param1 sets a clock source. The clock source in the FFT DMA example is set to timer 3 hard code. You want to change it to back to the default given in the ADC example, which is timer or clock auto, I think.
Yeah. This particular parameter here caused us a lot of trouble in one group.
Yeah, so it's ADC clock auto. Look 3 lines above.
Yeah. So you want to replace this with ADC clock auto. And if you really want to be safe, I'll just mention this again. As a starting place for setting up and configuring the ADC, use this example. Which you can see uses ADC clock auto. Sets you up on pin A and 11. Okay. And then this also shows you how to read the ADC in software. You'll do this in an interrupt service routine. In this example, it's being done in a thread, but same story. Let me see here. Okay, this is not a bug that many of you will likely encounter, but you might, depending if you want to work sort of beyond the goals of the written goals of the lab. Be aware that in the FFT, how do I want to phrase this? Okay, the FFT example code uses DMA channel 0 to read the ADC. Your serial thread that you use to communicate with the Python GUI also uses DMA channel 0. So if you want to configure your code so that you're not reading the ADC in an interrupt service routine in software, but instead you're using DMA to get samples from the ADC through a DMA channel, just be aware that if you want to combine that DMA code with the code that you use to interface with the Python GUI, you will need to change one of those DMA channels, And the easiest one to change is going to be the one that you use to read from the ADC. So if you want to read the ADC using a DMA channel and keep your Python GUI, change the ADC DMA channel to one other than 0. It's not particularly eloquently put, but I hope you get my point. The Python serial interface uses a DMA channel to facilitate that communication. The example FFT code uses a DMA channel to read from the ADC. Blindly putting them together isn't going to work because they're both configured to use DMA channel 1. So if you want them to work together, you need to change one or the other DMA channel, and the easiest one to probably change is the one that's reading the ADC. We did have one group do this.
Symptom is that the thread hangs because the DMA channel, because the FFT thread is watching the DMA channel complete flag. And if DMA channel 0 is being used for the Python, that flag is never set. And the system croaks.
The next thing that we've observed, which is, I'm sure you've all observed this, but I'm sort of letting you know that I have also observed it and I'm thinking about it, is the appearance of the spectrogram is much better when there are lights on in the lab. So the spectrogram is hard to see in dim light with the recommended color mapping. So I'm letting you know that I know that. And for the final project part of this course, when folks are, if you're working on a project that involves writing to the TFT display and the TFT display for your project looks better with lights on, we'll figure out some solution. The solution is probably going to be something like a desk lamp on your particular lab station, some sort of gentle light on your lab station just to make the visibility a little bit better. But I am aware of that issue. And it's interesting because depending on your project, you might want light or not want light. In Boyd's, we found that when you were drawing individual pixels, the high contrast introduced by having the lights off actually helped the visibility of single pixels. In this lab, it washes out the spectrogram. So let me know what is better for your final project, and we'll try to accommodate what works best for you. But I am aware of that. The other observation that was made is the cameras appear to be sensitive to super high contrast. So if you have a black background and white pixels, the image gets a little blown out. The pixels sort of get dilated and look bigger. And like I said, for some applications, that's good. For Boyd's, that was good because it made the Boyd's more visible. For the spectrograms, that's not good. So the other thing that you can experiment with is using a color map that has slightly less contrast. So perhaps instead of drawing on a black background, you draw on a sort of grayish background. That might improve visibility. So just keep that in mind. If you're having trouble with visibility and you're hypersensitive to light conditions, you might consider experimenting with less contrasty color maps for this lab and ultimately for your final project as well. You may experiment with less contrast, and that actually might improve visibility. Okay. Another thing I want to mention, like I said, it's kind of a long list. We have a lot of bugs in this lab. The recommended color map for the spectrogram is already log distributed. So in the example FFT code, there after the calculation of the magnitude of the complex output of the FFT function, there's a little snippet of code that's computing the log of that magnitude. You do not want that code in your spectrogram. for your spectrogram lab. And the reason for that is the color thresholds that we're choosing to select, the color thresholds that we're using to select the color for a particular pixel, those thresholds are already log distributed. So you are in effect sort of taking the log of the magnitude when you select those colors. If you calculate the log of the magnitude and then use that color mapping, you are doing log of log. And the result is going to be the whole spectrogram looks basically the same color. So just be careful of that. If you chose to take the log of the output magnitudes, you would have to change the color thresholds. Don't do that. I mean, you could if you wanted to, but there's no reason to do that. Just don't take the log of the output magnitudes and use the recommended color thresholds. You can change the colors if you want, but use those thresholds and you'll get something that looks right. Looks like it makes sense. Okay.
Hunter, question. What does it mean that the colors are log adjusted or like they're log colors?
So what I mean is, let me just move my zoom window here. What I mean is this color table, these magnitude thresholds are distributed exponentially. 1, 2, 4, 8, 16, 32, 64.
Gotcha.
So those thresholds are already distributed in such a way that you are essentially plotting the log of the magnitude without taking the log of the magnitude.
Gotcha.
There's a trick, by the way, a relatively good approximation, this is just for your information, a relatively good approximation of the base 2 log of a binary number, am I getting this right, Bruce, is the location, the position of the upper bit?
Yeah.
Yeah. So, a little trick. We use that in 5760 for doing the Mandelbrot lab. Okay. Oh, this is a good one. One of the requirements for this lab and specifically for the week 1 checkout is computation of. I need to be careful with my language here. The frequency with max amplitude. So not the maximum frequency, but the frequency where there is the most power in your spectrogram. You need to compute that and display that in some way. You can display it on the TFT if you want. You can print it out through the Python terminal if you want. You may find, in fact, you almost certainly will find that there is a DC offset to the input to the ADC, and the result of that is in your spectrogram, you will have a horizontal line at 0 hertz. That is the DC component of the input signal, which we aren't really interested in. So if you're not careful about this and you compute the max frequency, what you'll likely get as an output is the frequency with max amplitude will always be 0 hertz. And you'll go, what the hell's going on? I'm using this tone generator, I'm putting in 400 hertz, whatever it may be, and it's always 0 hertz. It's because there's a DC offset. So if when you do your frequency calculations, you do not include, your max frequency calculations do not include the bottommost bin, the bottommost index of the output array, or perhaps even the bottom few bins, then the output max frequency will be what you expect for it to be. So just be aware that there is a relatively loud DC offset to the analog input, which will mess up your max frequency calculation. So don't include index 0 of the magnitude array in your max frequency calculation. And by the way, this max frequency calculation, I've gotten some questions about this. the output of your FFT is arranged, is frequency arranged. Okay, so each index of the output array corresponds to a range of frequencies, where index 0 goes from 0 hertz to something greater than 0 hertz. It's some range of frequencies. Index 1 is the same range of frequencies, but goes from the upper threshold of that to the next threshold. So when you do this max frequency calculation, the way that you'll do it is you'll loop through your magnitude array, and you'll keep track of which index, in which index of this array was the magnitude the greatest. And that is the index where you have max power. And then you need to convert that index to a frequency. And the way that you convert that index to a frequency is you simply scale it by your sample rate divided by the size of your sample array, which in your case will be 512. So suppose you're sampling at 5 kilohertz. Suppose you're sampling at 5 kilohertz, and you find that index 100 has the greatest magnitude value in it. Then you convert that index 100 to a frequency by taking 100 times 5,000 divided by 512. 5,000 divided by 512 is the amount of frequency contained within each index of your output of the FFT. And so it's a unit conversion. You're converting from array index to frequency. And I got the question too, because each of these array indices represents a range of frequencies and not a specific frequency, how should we handle that? Should we output the bottom of the range associated with the index with the max power, or the middle of the range? The answer is I don't really care. Just compute a frequency associated with that index. It could be the bottom frequency associated with that index, it could be the top frequency associated with that index, or it could be one in the middle. Any of those is fine. And what you will find is the accuracy with which you can report the max frequency will improve as the frequency range of your spectrogram decreases. And it's because there's less frequencies per bin in the output. So you can put in a constant tone at 400 hertz, and if you sample at 10K, you'll get some answer for max frequency which has a certain amount of error in it. As you slide your sample rate down to, say, 2 kilohertz, you will find that your computed max frequency is closer to what you expect for it to be. 400 hertz was, I think, the example I used. Make sense?
Hunter, one question. If you see the max magnitude at 100, the 100th index,
Mm-hmm.
because of the reflection, do you expect it to see at 356 also?
Yes, you would. Yes, you would. Yeah. Okay. Something else. So some other tips that might just help you with debugging. If you are doing quite high-speed prints, which generally speaking isn't a great idea, but if you are doing high-speed prints to help with your debugging, those we have found can crash the Python interface. But if you open a PuTTY connection to your PIC32, that PuTTY connection is quite stable for higher speed printing. So if you are doing high-speed prints that are crashing Python, try PuTTY. Folks know what PuTTY is? Just show you quickly. It's already installed on all your lab PCs, but PuTTY allows for you to open a serial connection to a particular COM port at a particular baud rate. I don't have anything plugged in right now, so I won't open one, but you would put in whatever COM port your serial connection to your PIC is here, and the baud rate, which would be 115200 for you all here, open a connection, and then you can it'll stream the data out of the PIC. Much like your Python interface does, but in a different interface.
Hunter, I tried using PuTTY, but when I was using PuTTY, it didn't allow me to use my Python interface.
That makes
Oh,
sense.
sure.
So, like, I mean, it doesn't help much while debugging because we can't interact.
Well, it depends how you're debugging and what you're debugging. If you are debugging something that you don't need to interact, but you would benefit from some high speed printing, then it might be a good trade to set the Python interface for a while and use PuTTY, and then go back when you want to be interactive.
Okay.
My guess is that by the time you get around to trying to debug the maximum frequency slider, you're going to be way past the point of high-speed prints. The reason the Python crashes is that it's an interpreter. It's relatively slow compared to the hardware interface. And the reason it crashes is that you're filling a buffer of finite size that Python maintains. And you could try changing that, but PuTTY is much easier.
Okay. So this is my list of bugs that I've observed. Is there anything anyone would like to add to this list? Okay. Just keep an eye out for these things. If you didn't encounter one of these bugs consciously, then great. If you didn't encounter one of these bugs because you just happened to dodge a bullet, then perhaps this will help you avoid those bullets in the future. Okay, so unless there are questions, I want to next just briefly revisit some of the motor stuff that I was talking about last time, because that got a little abbreviated. So I just shared this window. So let me stop screen sharing and share this window. So these are the slides that I was going to include with the discussion that we gave last time. Zoom is in the way. I get it out there. So I'm not gonna go back over stuff that we already talked over, but there were a few things in these slides that I just neglected to mention or went a little too quick through. I'll just very briefly remind you that we were talking about the internal mechanisms of DC motors and the way that the way that in particular a brushed DC motor works. The mechanism by which it works is you set up some static magnetic field within the motor. You have a commutator here, which is essentially a ring-shaped brush where the bristles of that brush are conductive elements, and this armature can spin on top of that commutator. So it's free to rotate, but electrical connectivity is maintained. And the idea is we can pass DC current through this armature, which is coils of wire. We pass DC current through this armature. Current through a conductor in a magnetic field experiences a force. The force on one side of the armature is in one direction, the force on the other side of the armature is in the other direction, which causes a torque, and the whole thing rotates. This is the mechanism that we were talking about. One of the things that I forgot to mention is I mentioned that the model that we use to describe, a common model used to describe these DC motors is a DC motor looks kind of like a resistor in series with an inductor in series with a generator. And I mentioned that this inductance comes from the fact that generally speaking, windings exist somewhere in this motor, perhaps in the armature. In some motors, perhaps you're using an electromagnet, coils of wire to set up the stator field. There are windings in there. Those windings have inductance, so there's an inductor in here. There's resistance, so there's a resistor in here. And there's this generator. And the inclusion of this generator comes from an effect that I'm sure you've all heard of, which is back EMF. And I wanted to just talk sort of conceptually about what back EMF is, because it's interesting and useful, and it's one of these things that kind of has a negative connotation, it seems. When people talk about dealing with motors, back EMF, at least in my experience, people are like, it's annoying. So let me just explain what's going on. What back EMF is doing is it is setting up current opposite of the direction that you are sending current into the armature. And it's acting essentially as a feedback mechanism to control torque. So the armature, we know, is a conductor moving through a magnetic field. When you have a conductor moving through a magnetic field, there's an EMF induced on the armature as in a generator, right? So the motor, as you're turning it, is also acting like a generator. The way that a generator works is you spin a coil of wire inside a magnetic field and it induces current on the coil, which you can then get out and use for power. That exists here too, and that effect is also taking place. So as we are passing current through this armature and it's spinning, an opposing current is being generated on the armature, which is opposing the flow of that current and well, it's doing exactly that. It's opposing the flow of the current that you're putting in. So what's interesting about this is the faster the armature is rotating, the faster that coil of wire is spinning within the magnetic field, the greater the back EMF. So this is acting as a regulator for the current flowing through the armature. And when the motor is running under relatively normal conditions, the back EMF and the applied voltage are approximately equal to one another. They're opposing one another. So you have something like an equilibrium going on. What makes this interesting and useful is suppose you have a DC motor spinning happily at a constant rate, and then you grab the armature and slow it down. The effect of that is going to be this armature is rotating less quickly, so you generate less back EMF. There's less current opposing the applied current. So the current that is passing through the armature from the power supply increases. So the torque increases, right? So you grab it, you slow it down. When you slow it down, there's less back EMF. Because there's less back EMF opposing the current that you're putting into the armature, more current goes into the armature, which generates more torque and fights back against you. So when you try to slow down a DC motor, it automatically, because of this sort of built-in back EMF regulation, it automatically increases its torque output to compensate. And the opposite's also true. If the load on the motor is suddenly decreased, okay, so say you're holding the motor and opposing it, it's still spinning, but you have slowed it down and then you let go. What happens is suddenly that armature is spinning more quickly, so suddenly there's more back EMF, so there's more current opposing the current that you're applying, and the torque decreases and the speed increases. So there's this automatic mechanism of regulating the current through the motor, and that mechanism for automatic regulation is this back EMF. Make sense? So that is why in our model of the motor we have this generator here, which will generally always be generating a voltage equal to or less than the applied voltage. That's not true of the inductor, right? We talked about those big LDI/dt spikes. That will produce brief, huge voltage spikes in the opposite direction, right? This generator, which is we're using to model the back EMF, the voltage generated by that generator, by that back EMF, will always be less than or equal to the applied voltage here. Make sense? And let me just show you some pictures of stuff I was talking about yesterday and waving my hands at. We talked about the necessity for these snubber diodes being a consequence of the fact that there is inductance in these motors. And this is just a picture of what I was waving my hands at yesterday. And what you can see is if we have some inductor here, the voltage across that inductor is modeled by LDI/dt. Suppose we have something like millihenry inductance, and suppose we are using a transistor to very rapidly switch current off from this motor, then you can see that you get voltage that is reversed in polarity and very large for a brief amount of time, which is why we have that snubber diode. So the current is free to safely go in a loop here and doesn't damage other parts of the circuit. Okay, we talked about this. I think I hope that the little demo made the benefit of a bypass cap clear. So this is acting as a short for high frequency stuff. This motor's kicking out a lot of high frequency noise. This is attenuating some of that noise by providing a path to ground. And we looked at this circuit, so I'm not going to talk much about that. The other thing I wanted to just briefly mention, I imagine at this point in your classes here, you will have all worked with H-bridges before, so I imagine that you're all familiar with this circuit. An H-bridge is a common circuit used to drive current through a DC motor in one or the other direction. So it's composed of 4 transistors, 2 P-type transistors, 2 N-type transistors. And the notion is these are acting like switches, right? So you could think of these in your mind just as switches. And the idea is that if this switch and this switch are open, no current can flow, and this switch and this switch are closed, then current passes through the motor in this direction to ground. If the other 2 are closed and the other 2 are open, then current flows in the other direction through the motor, which allows for you to turn the motor in either direction. And if you're pulse width modulating these transistors, then you can turn the mode at a controllable speed in either direction. Something to be aware of. If this and this are both closed, what happens? Nothing good. Maybe your power supply blows up, I don't know. But you're shorting power to ground if you close these 2 transistors. So you can, and perhaps in some of your classes you have built these H-bridges yourself and controlled them in software. Boy, is that risky. That is really, really risky. Generally speaking, you buy an H-bridge, an integrated circuit H-bridge, which has built-in protection against it keeps you, the dumb user, from destroying your electronics by closing 2 of these switches at the same time, and only allows for you to open the appropriate switches at the appropriate times. It locks you out from doing things that would damage your circuit. So you can build these yourself. A lot of you likely have. I know that those of you that have taken mechatronics have built these yourselves and manipulated them in software. If you're building something for a company, probably that's not what you're going to do. Probably not. It's just too high risk. Questions about H-bridges? Like I said, I think folks have familiarity with these, so I won't dwell on them for too long. Just want to remind you that this is, if you're talking about DC motors, usually you're also talking about H-bridges. Okay. And then I wanted to show just a little picture. We talked just a little bit about stepper motors as being something that is sort of a different kind of motor that's suitable for a different sort of set of applications. And I waved my hands a little bit at the mechanism. And I wanted to just show you a very low fidelity picture of how the mechanism here works. So what I'm showing you here is we have 2 metal cores here. In reality, in a stepper motor, there could be hundreds of these, right? And each of these have a coil of wire wrapped around them. The idea being, depending on the direction that we pass current through these coils of wire, we can magnetize these cores in one direction or the other. So we pass current in one direction through this wire, this becomes a north pole and this becomes a south pole. Pass it in the other direction, this becomes a south pole, this becomes a north pole. And we can do the same with these cores. So in this configuration, you could imagine that we are passing current through this wire here, such that we are setting up a south pole here and a north pole here, which is holding this internal rotating permanent magnet in a stable configuration. It wants to just sit, right, with the north attracted to south and south attracted to north. If you were then to stop inducing polarity into this core and instead induce a south pole here and a north pole here, you could imagine that this permanent magnet would click into a new stable orientation. And in a stepper motor, there are, well, depending on the stepper motor, there's a different amount, but generally speaking, there are lots and lots of these stable configurations that you can step through. They're often separated by, I was looking at data sheets this morning, saw a few that were separated by like 1.8 degrees. So you can click 1.8 degrees, click, 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 click. Some are separated by 7-ish degrees, some by 15-ish degrees. So different quantizations of a full rotation. But this is the general idea, is you click from one orientation to the other orientation. The couple of advantages being that once you're in a stable configuration, you know pretty well, even without feedback, the position of the motor. So you can position these things quite accurately without requiring feedback, which is nice for some applications. The other nice thing about these is They are quite high torque at 0 RPM. So when you click this from this stable orientation to the next stable orientation, it really wants to twist, right? So if you're really interested in twisting something that requires high torque at low speed, a stepper motor might be what makes sense for that. And they are generally classified by the amount of wires that come out of them. You can have 4-wire stepper motors, which is kind of what's illustrated here. See, there would essentially be a control input to each of the outputs of these coils of wire, which you would send pulse trains to configure which coil is on and in which direction is current flowing through that coil. There are also 6-wire versions, which are center tapped here. So there's an additional control wire coming out of each of these coils that is generally held high. And then you would manipulate the outer wires to control which direction current flows through half the coil. You can determine the pinouts of these pretty easily with a multimeter. Say you have a 4-wire pinout, right? You can measure the resistance between the various outputs and say, okay, these have infinite resistance between them, so they aren't connected. These two are approximately shorted. So you can figure out the pinouts in that way. Okay. Any questions? Okay. Then with the remaining time, we only have a couple minutes left, so maybe I'll save the bulk of this conversation for another time. But like I briefly mentioned at the beginning of this lecture, towards the end of the semester for this class, as we enter final projects, we're going to transition from, unless there's opposition, unless people want to continue to have lectures, but usually what we do is we transition from lectures to, I will schedule more lab sections during the week where instructors will be present. And this is so that we can help you with your final projects. And at that point in the semester, that is usually the most helpful thing we can do, is just spend more time in lab with you. As we transition to that, just keep in mind that this remains a 4-credit course. So the expected amount of hours per week that you put into this course doesn't change when we transition from lectures to labs. So you'll be expected to put in something like 12 hours of work in lab per week. And in order to help you for that, we will add more instructed lab sections, but you'll have to put in time outside of those scheduled sections as well. So we'll talk more about that. I think that transition will likely take place sometime perhaps near the end of next week, when we're partway through Lab 4, I think, and starting to transition into final projects. So in the meantime, in the remaining lectures, I'll talk about Lab 4, and I think it makes sense to perhaps have one more group discussion about final projects, kicking around ideas and talking a little bit more about logistics. There's some things to think about with final projects, as far as it is up to you whether you or not you want for your project information to be shared publicly on the course website. And there are some reasons you might want that and some reasons you might not want that. And we'll talk through those various reasons. The only reason you might not want it is if you want to patent anything that you were to build in this class. That would count as an IP disclosure, and it starts a 1-year clock where you got to get that patented. So it's not a decision that you have to make at the beginning of the final project. It's one that you can delay until the end of the final project. But I just want to put it in the back of your head as something to be thinking about a little bit. If you work through your project and you think, this would make a pretty cool little product, it happens in this class, then just let us know and we won't share it publicly. And then that doesn't count as an IP disclosure. Any questions?